Some of our solar system's planets have been visited by scientific probes less frequently than others. The outer gas giants, Uranus and Neptune, are so distant they're hard to reach. Uranus is 20 times further from the Sun than Earth, while Neptune is 30 times further. Both have only been seen at close range by NASA's Voyager 2 spacecraft. Mercury is so close to the Sun that any probe sent in its direction must take a circuitous path to offset the Sun's immense gravitational influence. The Mariner 10 probe flew past Mercury in 1973, and the Messenger probe went into orbit around Mercury in 2011. Venus presents different problems. Though it's our closest planetary neighbor and easier for spacecraft to reach, dense cloud hides its features and its surface has hellish conditions. The Russian Venera craft have landed, but in the hostile environment, they could only survive for minutes. Roughly twice every century, the planet Venus passes between the Earth and the Sun. Called the Transit of Venus, it was closely observed in 1769. Astronomers realized that careful timing of Venus's passage across the face of the Sun would allow them to calculate the distance to the Sun, which in turn would unlock far more accurate methods of navigation. In 1961, the Soviet Union launched Venera 1, the first Venus probe. It passed Venus as intended, but mission control had lost contact with it. The following year, NASA launched Mariner 1 to Venus.
Not on trajectory.
A coding error led to control problems with the launcher.
Destruct command.
It was destroyed minutes after liftoff.
This apparently blew up.
Because convenient launch opportunities only occur in 18-month cycles, NASA had a second probe ready to launch. Mariner 2 was essentially a Ranger spacecraft designed to go to the Moon. These were the early days of the space race, and the United States was desperate to catch up with the Soviet Union. Lead times were short, and the Jet Propulsion Laboratory did not have time to complete its original design. In August 1962, Mariner 2 was launched. The Ranger spacecraft launched toward the Moon had all failed. Mariner 2, on its way to Venus, was functioning, but its transmissions were weak, and due to a launch anomaly, it was off course. After a week, instructions for a complex course correction were transmitted to the spacecraft. About an hour later, Mariner executed the maneuver, which involved a roll turn, followed by a pitch turn, and finally a main engine burn. It worked well, but several days later the craft lost lock on the Sun and the Earth, its two attitude reference points. It corrected itself before ground control could diagnose the problem. Next, the signal strength increased to its normal level, but a short in a solar panel left it low on power. At this time, although both America and the Soviet Union had been sending probes toward the planets, nothing had succeeded. Mariner 2 lost several telemetry sensors and it began to overheat. It continued limping toward Venus, but some of the spacecraft's problems were solving themselves. Mariner 2 was now close enough to the Sun that it could function effectively on just one solar panel. It passed slightly less than 35,000 kilometers above Venus's cloud tops. It could detect no planetary magnetic field, and it recorded temperatures across the planet approaching 500 degrees Kelvin. Clearly, landing on the surface would present problems. But America wanted to focus on their first real success in space, finally doing something that the Soviets had not. Mariner 2 was the first successful interplanetary probe, and in California, the home of JPL, they celebrated. The next major advances in the exploration of Venus were made by the Soviet Union. The objective of the Venera series was to land on the surface of Venus. Designers understood that not only were the surface temperatures hot enough to melt lead, but that the atmospheric pressure was many times that of Earth. The landers they built looked more like diving bells than spacecraft. In June 1967, Venera 4 was launched. The vehicle consisted of a carrier craft with instruments used during the cruise phase to Venus and a spherical landing module that could communicate independently. After entry into the atmosphere, Venera 4's parachute opened. It sent back data for 93 minutes, but stopped 28 kilometers above the surface. Yet its electronics hadn't been overwhelmed by the heat. It had simply run out of power. Extrapolations from its final measurements showed a surface temperature of 500 degrees Celsius and a pressure of 75 atmospheres, far higher than anyone expected. The Venera program strengthened its landers and fitted smaller parachutes to reduce descent time. Launched in January 1969, Venera 5 and 6 learned more about the chemical makeup of the atmosphere, but neither remained functioning at the surface. The Venera series continued, refining the technology and making incremental improvements to mission duration, adding to the knowledge about Venus. In 1975, Venera 9 was launched. It was a new design, consisting of an orbiter-lander combination, with the orbiter able to act as a relay station for signals transmitted from the surface. 4 months after launch, the orbiter and the lander, encased in a spherical shell, separated. It entered the atmosphere 2 days later, while the mother craft became the first probe to go into orbit around Venus, photographing parts of the surface in ultraviolet. The new lander had a ring shield that could replace a parachute during the latter stages of the descent through the dense atmosphere. Venera 9 transmitted the first black and white pictures from the surface, though a design fault meant a second camera could not eject its lens cap. 3 days later, and 2,000 kilometers away, a twin craft, Venera 10, landed. It took pictures too, but the same design fault left a lens cap stuck in place. Both landers had been pre-cooled while still in space, and circulating cooling fluid kept the craft operating on the blistering surface for more than an hour. In 1983, 2 more Venera craft arrived at Venus. Equipped with synthetic aperture radar, they made the first serious attempt to map the surface beneath the cloud layer. Over 8 months, they mapped from the North Pole down to 30 degrees north.
T-minus 10. 9, 8, 7, 6.
NASA had taken a minor role in the early exploration of Venus. But in 1989, the space shuttle Atlantis lifted off carrying the Magellan probe. Magellan was bound for Venus. Like the Venera craft before it, Magellan would use radar to map the surface of the planet. It was the first interplanetary spacecraft launched from the space shuttle. Following a cruise of 15 months, Magellan arrived at Venus and entered an elliptical orbit. To keep costs down, the probe had been built from an agglomeration of spare parts left over from previous NASA missions. After some software problems, it began mapping. The images it relayed remain the highest resolution pictures we have of the surface of Venus. Pictures of low volcanic blisters emerged, and lava channels were evidence of an extremely active surface. The thick atmosphere has prevented all but the largest meteors reaching Venusian ground, and few impact craters were visible. Yet evidence of plate tectonics that sculpts the Earth's surface was not obvious. After mapping Venus, Magellan changed its orbit and plotted the planet's gravitational anomalies. On Venus, localized changes in gravity correspond to surface features. On Earth, this is not the case. A new naked picture of Venus emerged. The surface appears to have been completely remade around 500 million years ago. Yet while volcanoes and lava channels are common features on Venus, Magellan could not find evidence that volcanic activity still happens on the planet. In 2006, the European Space Agency's Venus Express went into orbit around Venus. Its focus was the long-term analysis of the planet's atmosphere. During its 8-year mission, it registered a sharp rise in the atmosphere's sulfur dioxide. This could be due to changes in wind patterns, but it could also be a sign of volcanic activity. Researchers also saw increases in infrared radiation coming from 3 different volcanic locations. More circumstantial evidence of current volcanic activity. Finally, the infrared team saw short-term temperature changes that fluctuated over just a few days. It appears that volcanoes may still be active on Venus. The mission ended in 2015 with a series of swoops into the upper atmosphere that verified unexpected ripples in the mesosphere. Very little in the way of Venus exploration has happened since Venus Express. Though elaborate plans exist for future missions to Venus, nothing at this stage has been funded. Yet many missions still pass close to Venus to use its gravitation to alter their flight paths. In 1974, Mariner 10 was the first spacecraft ever to use the gravitational slingshot effect on its way to Mercury. Italian mathematician Giuseppe Colombo devised the maneuver as a way to save fuel and to fly past Mercury not once but several times. The technique is now commonplace. 10 days after launch, Mariner 10 executed instructions for a routine course correction. This appeared to go well, but after the burn, when the craft attempted to reorient itself, there was a problem. Mariner 10 knew where it was pointing because its tracking sensor could lock onto the star Canopus, but a flake of paint that had come from the spacecraft was confusing the system. An automated backup procedure found Canopus again, but flaking paint was an issue for the rest of the mission. To reach Mercury, a spacecraft must approach the Sun, and its immense gravity presents a problem. Voyages to outer planets are constantly slowed by solar gravity, but with the inner planets, a spacecraft constantly accelerates. Mariner 10 used Venus's gravity to reduce its speed, and it approached Mercury at an acute angle. Mariner 10 did not have enough fuel to go into orbit around Mercury, but its sun-centered path allowed the probe to make 3 close passes. Its first pass revealed a moon-like planet with a heavily cratered surface. Though Mercury is the smallest planet, it's the most dense. It has a large, iron-rich core. Prominent escarpments were seen. Here, Discovery Scarp cuts through 2 craters. It falls 3 kilometers. It's thought that these cliffs are the result of cooling and shrinking of the core. Mariner 10 continued to suffer technical problems. Its tape recorder kept sticking. There were restrictions in the rates of data transmission, and limited attitude control meant flight engineers were using solar pressure on the high-gain antenna and solar panels to compensate. Yet the mission continued. Mariner 10 could only map about 45% of Mercury's surface, as the same hemisphere faced the Sun during each of its passes. Mariner 10 discovered a very thin atmosphere, primarily of helium. Several months after its third and final pass of Mercury, it ran out of fuel. It still orbits the Sun.
Main engine start, 2, 1, and 0.
It was more than 30 years before the next mission to Mercury. In 2004, Messenger was launched. It was designed to go into orbit around Mercury, which presented a number of design constraints. It featured a large woven ceramic sun shield, but it did not have a dish antenna. It would rely on a phased array that could be electronically pointed. After a year in space, Messenger was back at Earth, using its gravitation to modify its orbit. Even though it was not a large spacecraft, it had a powerful engine for course corrections and orbit insertion. It continued on to pass Venus twice to lose speed as it drew closer to the Sun. 3.5 years after launch, Messenger approached Mercury, but this was not the end of its journey. The probe made 2 more passes of Mercury before finally going into orbit after almost 7 years in space. Mission engineers had the extra problem of always requiring the probe's sun shield to be pointed toward the Sun. Because it was in orbit, Messenger was able to complete the mapping started by Mariner 10. The planet's dominant feature is the Caloris Basin. It's an ancient crater more than 1,500 kilometers across. Mariner 10 saw some of the area, but the rest had been in darkness. This map of the southern polar region uses color to represent illumination. Because Mercury's axis is not tilted, sunlight cannot penetrate deep craters near the poles. It was in these areas that Messenger discovered substantial amounts of water ice. Messenger received several mission extensions, but in 2015 it crashed into Mercury after running out of fuel. A new mission is already on its way to Mercury, Bepi Colombo, named after the designer of Mariner 10's trajectory. It's a joint effort between JAXA, the Japanese space agency, and the European Space Agency. It will take 7 years to reach Mercury. The Voyager 2 spacecraft is the only probe to have made close approaches to the 2 outer ice giants, Uranus and Neptune. Launched in 1977 with its twin Voyager 1, it was able to take advantage of a rare alignment of the 4 outer planets, enabling it to make close observations of each one. In 1986, Voyager approached Uranus. In the distant past, it must have been hit by another massive body that knocked its axis sideways. Uranus has an east and a west pole, and for half its orbit, one side sees continual sun, while the other remains in darkness. It has rings which follow its north-south equator. Voyager 2 discovered 11 new moons and a misaligned magnetic field. Images that the Voyager captured showed Uranus as a bland, featureless planet, but this was because of its particular season. With images from the Hubble Space Telescope, we now know that at certain times clouds and planetary weather appear in the atmosphere. Uranus's largest moon, Miranda, was observed in detail for the first time. So chaotic is its surface that researchers thought that it must have been blown apart by some cosmic impact, with the fragments reforming. Now it's thought that tectonic forces, initiated by the gravitation of Uranus, are responsible for the moon's jumbled appearance. As Voyager 2 left Uranus, backlighting from the sun revealed two new rings encircling the planet. The spacecraft was now heading toward Neptune, the solar system's last planet. In the 3 years it would take to get there, ground engineers began preparing for unique challenges. Neptune is 30 times further from the Sun than the Earth, and the light intensity is 1,000th what it is here. For photography, time exposures would be necessary, yet Voyager 2 was traveling so fast that images would smear without special preparation. Engineers calculated just how much the craft would have to swivel while exposures were made to compensate for the probe's movement. In June 1989, Voyager 2 began returning distant images of Neptune. Across the world, people had realized that the data sent back to Earth by this spacecraft was transforming our understanding of the solar system. This was before the internet age. Researchers at the Jet Propulsion Laboratory clustered around TV sets to watch as data and images came in line by line. Neptune is a more conventional planet than Uranus. Its axial tilt is 30 degrees, and it revolves in the same direction as Earth. While Neptune is slightly heavier than its fellow ice giant Uranus, it has a slightly smaller diameter. And, though it is further from the Sun than its neighbor, Neptune emits more heat than Uranus. The planet has an internal heat source that drives more dynamic weather patterns. Voyager 2 measured wind speeds at Neptune in excess of 2,000 kilometers per hour, the fastest in the solar system. There were cirrus clouds in the atmosphere, and the probe recorded pictures of a great dark spot, similar to Jupiter's Great Red Spot. It was an anticyclone in the southern hemisphere as large as the Earth. In 1994, when Hubble tried to find the same feature, it had disappeared, but a new dark spot was forming in the northern hemisphere. Voyager 2's last observations within the solar system were of Neptune's largest moon, Triton. Unlike all other moons in the solar system, Triton has a retrograde orbit, indicating that it was not formed at the same time as the planet, but that it had been captured. As Voyager 2 moved beyond the planets, its cameras were switched off to save power. Both Voyagers continue away from the solar system, measuring the influence of the solar wind. This remains the only mission to the ice giants. On January the 19th, 2006, an Atlas V was launched. It was a very powerful rocket with an unusually small payload. New Horizons left Earth orbit faster than any other probe. It was headed for the Kuiper belt at the outer edge of the solar system, in particular Pluto. In a little more than a year, New Horizons reached Jupiter, where it received a gravitational assist that cut 3 years from its flight time to Pluto. After it passed Jupiter, the spacecraft went into hibernation, simply sending an "all's well" transmission once a week. It took New Horizons more than 9 years to reach Pluto. Since it had departed, Pluto had lost its status as a planet. With the discovery of more objects of similar size in the Kuiper belt, it was decided that to be a planet, a body had to clear its orbit. Pluto's features surprised everyone. Here was a living planet shaped by tectonic forces, but instead of rock, the mountains were made of ice and frozen methane. And Pluto has a thin atmosphere, mainly of nitrogen. The probe continued on over Charon, Pluto's largest moon. Its icy surface has deep canyons, and some evidence suggests that it has ice volcanoes. Charon is about half the size of Pluto, and the two orbit each other. From Pluto, Charon would appear motionless in the sky. As the New Horizons probe sped away from Pluto into deep space, it began the slow process of transmitting its recorded data back to the Earth. At these distances, it takes signals 4.5 hours to reach Earth, with data coming in at 1 kilobit per second. It took 469 days for all the Pluto information to be received back on Earth. Early in 2019, New Horizons passed trans-Neptunian object Ultima Thule, and with a mission extension, it continues exploring the outer reaches of the solar system. For a human to work in space, he or she must have a spacesuit. It protects the astronaut from the vacuum beyond the atmosphere, supplying oxygen as well as insulation from the extremes of heat and cold. The spacesuit has to have means of communication with the outside world, and it must enable freedom of movement. The modern spacesuit is the result of a long and complex evolution. Long before humans had traveled to space, aviators wanted to fly at heights that could not support life. In 1932, Auguste Piccard flew above 16,000 meters in a helium-filled balloon. To stay alive, Piccard ascended in an aluminium pressure vessel fed with compressed air. Spanish aviator Emilio Herreras came up with a different solution. His stratospheric suit never flew. It was an idea ahead of its time. In the United States, aviator Wiley Post had supercharged his plane, the Winnie Mae. It could fly at 15,000 meters, where the jet streams blow. Post knew he could save fuel and fly faster at that height. So with the help of tire maker B.F. Goodrich, he devised the first serviceable pressure suit. At this time, even military aircraft were flying at much lower altitudes, where the use of a simple oxygen mask was enough to ensure pilot efficiency. However, as jet power was introduced, operational ceilings lifted, At high altitudes, low ambient air pressure meant the oxygen mask would lift off the face when oxygen was fed to the pilot at pressures high enough to sustain life. When bombers like the B-36 began long-duration missions at high altitudes, they adopted pressurized crew compartments. Yet the pressure suit, with a fully enclosed helmet, was necessary as sudden cabin depressurization could be lethal. In the 1950s, partial pressure suits became common. They had inflatable capstans that stopped blood draining to the legs under heavy G-forces, avoiding blackouts. Air crews hated them, but figures showed they functioned more effectively when wearing them. In 1955, a unique American spy plane made its first flight. The following year, the U-2 began reconnaissance missions over the Soviet Union. Flying at 21,000 meters, it was beyond the range of Soviet radar, and neither jet fighters nor missiles could reach it. Pilots flying the U-2 wore a new partial pressure suit, the MC-3. Rather than save a pilot's life in case of sudden depressurization, this suit was designed to be under pressure throughout the mission. Without it, the pilot's blood would boil. As missile technology developed, it appeared that human beings would be dispensed with as a weak link, not able to cope with conditions imposed by the technology. But the US Air Force had different ideas. They felt that a pilot could make better decisions than a guidance system, and they began a research program using hypersonic aircraft to learn about the problems associated with ultra-high speed, ultra-high altitude operations. The culmination of this program was represented by the X-15, a rocket-powered aircraft that could fly to the edge of the atmosphere. Because of its limited fuel load, the X-15 was launched from beneath a B-52 bomber at an altitude of 15,000 meters. The cabin of the X-15 was pressurized with nitrogen to reduce the risk of fire. For the pilot, a new full-pressure flight suit, known as the XMC-2, was developed. It too was pressurized with nitrogen. A neck dam excluded the nitrogen from the helmet, which was fed with oxygen for life support. This suit was the predecessor of NASA's most important spacesuits. The X-15 set the speed record for a powered aircraft at well above 7,000 kilometers per hour, and the altitude record at just over 107,000 meters. The first real spacesuit was worn by Russian cosmonaut Yuri Gagarin. In 1961, aboard Vostok 1, he became the first man to orbit the Earth. His suit, the SK-1, was to protect against capsule depressurization and to sustain him during ejection from his craft. The Vostok cosmonauts had to parachute to the ground because their capsules landed too heavily. Since 1959, the newly formed US space agency, NASA, had been working towards launching an American into space. 7 test pilots had been selected as the Mercury program's first group of astronauts. The first attempt would be a short hop. As the only booster available at the time, the Redstone lacked the power to reach orbit. An important part of the preparation involved the development of a spacesuit. As a starting point, NASA looked at the XMC-2 used for X-15 flights and the Navy's aviation pressure suit, the Mark IV. Both were full pressure suits. NASA decided that the Mark IV suit, worn here by Alan Shepard, was lighter and could be more easily modified for spaceflight. The boot leather and the suit's grey outer covering would be replaced by aluminized nylon for greater thermal control, and the helmet's rubber diaphragm surrounding the face was eliminated, with oxygen now entering via a hose at the waist to help cool the suit. For all 6 manned Mercury missions, the Mark IV suit performed well, but the demands placed upon it were modest. Like most pressure suits at the time, it served as a backup in the event of cabin pressure failure. Because this never happened on the Mercury flights, this suit was only ever pressurized at launch. In the early 1960s, the Soviet Union's space program was achieving an impressive list of firsts. For the United States, this was a source of national embarrassment. In 1961, the new president, John Kennedy, had boldly proclaimed that America should land a man on the moon before the end of the decade, and NASA was flooded with funds. This was the beginning of the space race.
I don't think we ought to waste any money, but I think we ought to do the job. And this will be done in the decade of the 60s.
The Mercury program was terminated early, in favor of a more complex series of missions with the aim of solving problems associated with sending a man to the moon. The Gemini program made use of a new 2-man capsule boosted to orbit atop a modified nuclear missile. Gemini required a new suit with new capabilities. NASA now understood future missions would have to last much longer. Suits would have to be more comfortable, and astronauts would have to leave their spacecraft in the vacuum of space. Gemini controllers were planning the first spacewalk. In the less open Soviet Union, they were also preparing for a spacewalk. Cosmonaut Alexei Leonov was practicing with an inflatable canvas airlock in temporary weightlessness in an aircraft in a parabolic flight path. He was wearing a new spacesuit, the Berkut, designed to function outside his Voskhod spacecraft. The airlock was needed because the new Voskhod still did not have solid-state electronics. Its thermionic valves needed air cooling so the capsule could not be evacuated. In March 1965, Alexei Leonov left the airlock on Voskhod 2 to float freely in space. It was another first for the Soviet Union. Soon, his Berkut spacesuit began ballooning to such an extent that Leonov could not reach his camera's shutter release, positioned on his leg. It was not until after the fall of the Soviet Union that the full story became known. The Berkut spacesuit had expanded so much that Leonov could not get back inside. Only by venting his spacesuit could the cosmonaut regain entry to the Voskhod capsule. Back at NASA, they heard that Leonov's spacewalk had been a resounding success, but they felt the Gemini program was catching up. In June 1965, astronauts Jim McDivitt and Ed White were preparing for the world's second spacewalk. Gemini 4's launch went smoothly, and on the third orbit, Ed White left the capsule. Although they didn't know it, the greater sophistication of the Gemini craft made this spacewalk much simpler than Alexei Leonov's just 2 months earlier.
Okay, I'm out.
It was easy to depressurize the entire capsule, so no airlock was needed, and Ed White's spacesuit was fed through an umbilical connected to the spacecraft. Leonov carried his own oxygen in a backpack that made re-entry to the Voskhod capsule that much harder. Within the structure of the Gemini suit was a mesh that prevented the ballooning problem experienced during the Russian spacewalk.
I'm just like $1 million.
The first American spacewalk went so well that NASA assumed working in space presented few obstacles. White's joyride in space gave no indication of the difficulties that lay ahead. The Gemini program had a number of goals. And in December 1965, Gemini 6A and Gemini 7 achieved 2 of them: rendezvous and long-duration flight. The crew of Gemini 7 remained in orbit for 14 days. Mission planners knew that staying in a spacesuit for 2 weeks would be a challenge. So a new version of the G3C spacesuit, called the G5C, was worn by the Gemini 7 astronauts. It replaced the pressure helmet with a zippered hood, and Frank Borman and Jim Lovell became the first people to remove their spacesuits in flight. New technologies were being pioneered in the Gemini spacecraft, and problems with the new systems often meant Gemini flights were only partially successful. The capsule had to be capable of far more complex maneuvers than its predecessor, and longer duration missions required fuel cell technology for electric power. In March 1966, Gemini 8 had successfully rendezvoused and then docked with a target vehicle. But a thruster problem sent the linked craft into a spin. The mission was immediately terminated. The scheduled spacewalk did not take place, and the craft landed in the Pacific, half a world away from the planned landing area. 3 months later, Gemini 9 could not dock because its target vehicle's fairing had not been jettisoned. The scheduled spacewalk went disastrously wrong. When Gene Cernan inflated his suit, it did not want to bend. Exhaustion and a fogging space helmet saw Cernan called back inside. He was overheating. Training for a spacewalk was limited to brief periods of weightlessness in an aircraft, or being suspended in a special jig that moved via an air suspension system across a smooth floor. Neither provided anything like the real thing. Engineers had realized that the current generation of spacesuit worked well sitting in a spacecraft, but when doing strenuous work, its air cooling system was inadequate. New designs were already in train. The next 2 Gemini flights both failed to demonstrate that an astronaut in a spacesuit could do meaningful work in space. Before the final Gemini flight, a new training simulation was tried. A mock-up of the Gemini craft docked to an Agena target vehicle was built in the McDonough School indoor pool. An approximation of the true weightless environment, it allowed astronaut Buzz Aldrin to train for extended periods. Handholds were fitted to the outside of the spacecraft, and the extravehicular work assignments on Gemini 12 were a complete success. It gave NASA planners the confidence to move to the Apollo program and the final stages in America's progress to its moon landing. By 1966, it was apparent that Apollo was well behind schedule. The first manned flight of the program had been delayed by almost a year because of developmental problems with the Apollo spacecraft. NASA was rushing to meet the 1969 moon landing deadline set by President Kennedy, and privately some in the astronaut corps felt that the hurry was not good for the development of a new capsule. NASA had flagged changes to later models of the spacecraft, but the early Block 1 version would still carry a crew in the first manned mission to test systems in Earth orbit. A new spacesuit was being developed for use on the later moon missions, but it would not be ready for Apollo 1, whose astronauts, Gus Grissom, Ed White, and Roger Chaffee, would wear a slightly different version of the Gemini GC-4 suit. All American spacecraft had been pressurized with pure oxygen. This had weight-saving benefits, and by exclusion of nitrogen found in natural air, the danger of bubbles forming in the bloodstream during rapid decompression was eliminated. Though the pure oxygen environment presented a fire danger, nobody had thought to check the real risks. In January 1967, Less than a month before the scheduled launch date, the Apollo 1 crew were in their capsule under simulated launch conditions, with the craft being tested under its own power. A spark triggered a fire, and in seconds the crew were dead. The inquiry into the fire found the astronauts had died of asphyxiation from carbon monoxide. Both the spacesuits and the cabin made extensive use of combustible materials. For the program to continue, everything would have to be redesigned. Research into the problems associated with a spacesuit that could be used on the Moon had been going on since 1962. The new suit had to be rugged. Designers were still not sure what the lunar surface would present. All previous suits had been fed with oxygen and power from an external source. The Moon suit had to be self-contained, and the backpack supplying life support presented problems. The backpack's dimensions and weight were determined by extensive testing, and designers of the life support, battery and communication systems worked within strict parameters. After the Apollo 1 tragedy, flammable components had been removed, and an outer layer of beta cloth, of woven silica fiber coated with Teflon, was added. Many different ways of simulating the Moon's 1/6 gravity were trialed. Finally, the A7L suit emerged. Beneath the outer layer, a tight-fitting suit with elbow, wrist and knee joints of a bellows-like structure that maintained equal volume when bent, allowed freedom of movement absent in previous suits. Beneath the pressure suit, a light open-weave layer was networked with fine tubes circulating cooling water. This carried away excess body heat that earlier air-cooled suits had not coped with. The pressure suit and the outer protective layer were joined together, with the inner cooling garment remaining separate. On Earth, the whole suit weighed 35 kilograms, with the backpack a further 60 kilograms. It was the A7L that went to the Moon with the first 3 successful Apollo lunar missions, and it performed flawlessly. It continued to evolve as subsequent missions became more demanding. The Moon suit was robust, and Apollo astronauts had complete confidence in it. No lunar mission ever had a problem with the spacesuit.
We have main engine start.
With the arrival of the Space Shuttle, NASA was expecting to do serious work in orbit, and it needed a new spacesuit. The Extravehicular Mobility Unit, or EMU, is a direct descendant of the Apollo A7L. Its main difference is the rigid upper torso. Because they are used in a weightless environment, the new suits could be heavier than the Apollo suit, which operated in lunar gravity. The EMU is not custom-tailored for each user. Components are made in a range of sizes and are interchangeable. Parts are intended to have a useful life of around 15 years. With the shuttle, NASA envisioned servicing satellites in low Earth orbit, but first it had to learn how to do simple tasks. New technologies were combined with the spacesuit. In 1984, astronaut Bruce McCandless, using the Manned Maneuvering Unit, flew independently beside the Space Shuttle Challenger. After 4 hours, he returned safely. The MMU was used for satellite recovery on 2 subsequent occasions, with mixed results. After the Challenger disaster, NASA reviewed all aspects of safety, and the MMU was retired as too risky. A simpler technique emerged. With foot restraints on the shuttle's robotic arm, astronauts could be moved accurately to a site and have a stable work platform. In 1990, the Hubble Space Telescope was launched. Unlike other satellites, Hubble was designed to be visited by the Space Shuttle for regular maintenance and upgrades. Over a 16-year span, there were 5 servicing missions to the telescope, the first being to fix an error in its manufacture.
Is a game-ending activity.
Each servicing mission called for long and complex spacewalks. The EVAs were all thoroughly rehearsed in NASA's Neutral Buoyancy Laboratory. The astronauts are weighted so that they neither rise nor sink, and all the large components that they handle are similarly neutral. Astronauts still have the perception of up and down in neutral buoyancy, unlike in weightlessness. In 1998, work commenced on the International Space Station, a collaboration between the US, Russia, Europe, Japan, and Canada. This was the type of project for which the Space Shuttle had been designed, and the expertise that NASA's astronaut corps had gained was to be put to use for on-orbit construction. As the space station grew, the EMU spacesuit was refined. Increased battery capacity was added so that small heaters in the gloves could keep astronauts' fingers warm during passages through the Earth's shadow. A new safety system was added to the EMU suits. Called SAFER, the simplified maneuvering system is designed for emergencies in the rare event that a spacewalker becomes untethered from the space station. It was first tested in 1994, but it has never been used for an actual emergency. With the completion of the ISS in 2011, the Space Shuttle was retired. This meant sole access to the orbiting laboratory was via the Russian Soyuz spacecraft. Cosmonauts and astronauts wear the Russian Sokol flight suit during trips to and from orbit. For maintenance and repair sorties outside the ISS, crew will wear either the EMU or the Russian Orlan spacesuit. Many of the Europeans on board have training in the use of both. The Orlan spacesuit is very practical, designed to be serviced on the space station. It has a rigid torso, with the helmet and visor joined to the suit, and access is via a rear hatch. Cosmonauts wear a water-cooled undergarment similar to the American suit. Unlike the American suit, the Orlan can be put on in just 5 minutes. In the MKS, the latest version of the Orlan, a cosmonaut can safely remain outside for 7 hours. And finally, NASA is working on a new generation suit to meet its future needs. Called the PXS for Prototype Exploration Suit, it also features a rear entry hatch. The PXS has a more advanced life support system and is lighter. A different version, called the Z2, is being developed for use on the surface of Mars. It allows a greater range of movement, and its life support system will take less time to recharge, although neither suit has yet been used in conjunction with its life support backpack. Jupiter is our solar system's largest planet. It's more than twice the mass of all the other planets combined. Its swirling atmosphere moves in bands at different latitudes, and its great red spot is thought to be a perpetual storm. Recently, images from a new probe that has flown above Jupiter's poles reveal a completely different planet. The ancient Romans knew Jupiter as the celestial representation of the king of the gods. In 1610, Galileo, using his newly improved telescope, saw Jupiter's moons and could see they orbited the planet, evidence that not everything revolved around the Earth as the Church had declared. Though better telescopes improved our view of Jupiter, it was not until 1964 that Gary Flandreau, a graduate student working part-time at NASA's JPL, understood there was a way to get a clearer look at Jupiter. By plotting the positions of the outer planets, he realized that a rare alignment would enable a spacecraft launched in 1977 to visit Jupiter, Saturn, Uranus, and Neptune. NASA jumped at the opportunity and began work on twin craft for what was then known as the Planetary Grand Tour. To limit any surprises, two basic spacecraft, known as Pioneer 10 and 11, were quickly built. They would go ahead of the Grand Tour missions to send back information about the environment. Pioneer 10 was launched toward Jupiter in March 1972. It was the first spacecraft to cross the asteroid belt that lay between Mars and Jupiter, and because it was the first probe on a trajectory that would take it out of the solar system, it carried a plaque identifying its origin. By December 1973, Pioneer 10 was sending back pictures of Jupiter clearer than anything that had been seen before. Approaching Jupiter, it encountered levels of ion radiation 10,000 times more intense than the radiation belts surrounding Earth. As the probe skimmed past the giant planet, it gained speed. Leaving Earth, Pioneer 10 was moving at 51,000 kilometers per hour. Departing Jupiter, it had more than doubled its speed. This gravitational slingshot effect made the Grand Tour possible. The Grand Tour craft, recently renamed Voyager 1 and 2, were due to be transferred to Cape Canaveral for launch integration when news of Jupiter's extreme radiation environment came through. The electron radiation at Jupiter had generated false commands within Pioneer 10. With the far more sophisticated Voyagers, this presented problems. Local supermarkets were stripped of their stocks of kitchen-grade aluminium foil, which was then used to shield critical cables. Without this last-minute alteration, electrical pressures of up to 40,000 volts would have been induced in the Voyager's subsystems as the craft passed Jupiter. Voyager 2 was launched in August 1977. Its trajectory meant that it could visit Jupiter, Saturn, Uranus, and Neptune.
To extend man's senses farther into the solar system than ever.
Voyager 1 left 16 days later. Its different, faster trajectory only allowed flybys of Jupiter and Saturn and various large moons. At the time, the Voyager spacecraft were the most sophisticated probes to be launched. Because they were to operate at huge distances from the Sun, solar panels could not be used as a power source. They were equipped with radioisotope thermoelectric generators, which use the heat from the decay of plutonium-238 to generate power. As Voyager 1 approached Jupiter in January 1979, it began sending image sequences that showed a complex and dynamic planet. The planet's giant red spot was revealed as a vast rotating storm. In 1665, Giovanni Cassini described a permanent spot on Jupiter which was regularly observed into the 1700s. It was not until the late 1800s that Jupiter's spot was described as red, and it's uncertain whether the historic observations of Jupiter's spot refer to the same feature or a phenomenon that regularly manifests in Jupiter's atmosphere. Voyager 1 made its closest approach early in March 1979. As the probe neared Jupiter, the activity at NASA's Jet Propulsion Laboratory became intense. This was the nature of the Voyager's flyby missions. There were long, quiet cruise phases between the planets, followed by brief periods when the flow of information from the craft overwhelmed researchers. One of the biggest contributions made by the Voyagers was the transformation in our understanding of the Galilean moons. Previously just dots of light, Jupiter's 4 largest moons were each distinct and completely different. The first surprise was the inner moon Io. It's a sulfurous yellow in appearance, and one particular long-duration exposure revealed an odd plume. Rather than being a cold, dead world, the gravitational squeezing Io receives from its giant neighbor heats the moon's interior. The plume was a volcanic eruption, ejecting material hundreds of kilometers above the surface. In July 1979, 3 months after Voyager 1 had moved beyond Jupiter, Voyager 2 made its closest approach. It was able to examine different moons more closely than its twin. Europa was the next surprise. It is highly reflective and has the smoothest surface of any body in the solar system. Further observation revealed pressure ridges reminiscent of polar ice flows on Earth. Europa is a frozen world, with a vast ocean beneath a thick crust of ice. Like Io, it is heated from within by tidal flexing. As Voyager 2 continued toward Saturn, planetary researchers were left with large amounts of raw data about Jupiter still to be processed. The Voyager missions left us with a basic view of the Jovian system, but they had raised more questions than they were able to answer. It would be more than 10 years before Jupiter received another visitor from Earth.
Ignition and liftoff of Discovery and the Ulysses spacecraft bound for the polar regions of the Sun.
In October 1990, the Space Shuttle Discovery lifted the European Ulysses spacecraft to low Earth orbit. From there, it was boosted on a mission to observe the Sun, but first, it would pass Jupiter. All the planets orbit the Sun in the same direction, in roughly the same plane. This is called the ecliptic, and it developed from the spinning disk of dust and gas that formed our solar system. The designers of the Ulysses spacecraft wanted to see the Sun from an orbit above its poles. Jupiter's extreme gravitation was used to bend the probe's flight path out of the ecliptic so it could make north-south orbits of the Sun. Ulysses was not the only probe to take advantage of Jupiter's gravity. Both the Cassini probe to Saturn, launched in 1997, and the New Horizons probe to Pluto, launched in 2006, were able to reduce their flight times by years with Jupiter flybys. These probes were able to make meaningful observations while passing the giant planet. In the clean rooms of the Jet Propulsion Laboratory, a new probe was taking shape. Galileo would be the first spacecraft to go into orbit around Jupiter. Its 4.8-meter antenna was folded like an umbrella, only to be deployed when safely on the way to Jupiter. Originally scheduled to launch in 1986, it sat in storage for years after the Space Shuttle Challenger exploded.
10, 9,
It launched aboard Space Shuttle Atlantis in October 1989.
4, 3, 2, 1. We have ignition and liftoff of Atlantis and the Galileo spacecraft bound for Jupiter.
New rules governing shuttle launches meant a change in the booster to push Galileo out of Earth orbit. The less powerful solid fuel upper stage, now stipulated, sent Galileo toward Venus for a gravity assist. The new flight path meant Galileo was traveling to a hotter part of the solar system. It was decided to keep the heat-sensitive antenna furled until after the spacecraft looped back past Earth. Galileo made 2 close passes of Earth, each time gaining more speed. Its first pass was in December 1990, more than a year after its launch. A further year on, when it passed Earth again, the high-gain antenna was only partially open. After months of trying different techniques to deploy the antenna, mission engineers concluded that long periods in storage had caused lubricant at the tips of the antenna's ribs to dissipate. Researchers would rely on Galileo's smaller antenna, with data delivered at slower rates. During the cruise to Jupiter, Galileo encountered several asteroids. This is Ida, the first asteroid we've learnt of with its own moon, Dactyl. In July 1995, while it was still 6 months away from its closest encounter with Jupiter, Galileo ejected a small probe designed to enter the atmosphere and sample its chemical composition. The probe lasted for an hour in Jupiter's atmosphere. The data was relayed to Galileo and recorded for subsequent transmission back to Earth. Its analysis revealed hardly any water vapor, which was unexpected, and other elements, particularly helium, were detected at far lower levels than predicted. The probe experienced areas of extreme heat and cold, suggesting heat is being released from the planet's interior. Slightly more than an hour after transmission from the probe ceased, Galileo began its orbit insertion burn. Its engine had to operate for 49 minutes to put it into a highly elliptical equatorial orbit. But this orbit would be altered with another burn at its high point. Mission designers were acutely aware of the high radiation environment, and the second burn would lift Galileo above the extreme radiation at its closest approach. Galileo's initial orbit eventually delivered a close approach to Ganymede, Jupiter's largest moon. During this orbit, engineers were trying to understand damage to the spacecraft's vital tape recorder. Without its high-gain antenna, the recorder was essential for slow replay of data recorded during the brief, close encounters. It had been stuck in rewind for 15 hours, and tape had been degraded. Light-emitting diodes, key elements in the recorder's control system, had acquired radiation defects. The second orbit also passed Ganymede. Galileo discovered it's the only moon in the solar system with a significant magnetic field. It also has an ocean sandwiched between two layers of ice. Galileo's orbits would be slightly varied so that it could make close approaches to different Jovian moons. But the equatorial orbits needed to reach the moons also took the craft through hotspots in Jupiter's radiation belts. With the observations made by the Voyagers, the moon Europa was of particular interest to the Galileo team. Data from several instruments agreed that a salty ocean exists beneath Europa's surface ice. Later examination of the Galileo datasets revealed plasma wave and magnetic field information, showing that plumes of water vapor were erupting from cracks in the surface. Europa has more water than Earth, which makes it a possible home to life. Io was already known to have volcanic activity, but Galileo saw tides in the moon's solid surface of more than 100 meters. The temperatures generated by this gravitational distortion of Io make its numerous volcanoes hotter than anything found on Earth. During its 8 years at Jupiter, Galileo completed 35 orbits, filling out our limited picture of the Jovian system. This was never an easy mission. Galileo was a robust spacecraft, but the radiation environment stressed all the subsystems, and engineers were constantly having to find workarounds for the frequent breakdowns Galileo suffered. Instruments showed increased noise when near Jupiter, and current leakages caused by radiation led to several resets of the onboard computer, with crucial loss of data. Software changes enabled the computer to recognize these resets and to recover by itself. Information learned would lead to changes in the way the next Jupiter spacecraft was designed.
5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter.
In August 2011, Juno began a journey to Jupiter that would last almost 5 years. Its mission parameters would be very different to Galileo's. It would ignore the moons and focus exclusively on Jupiter.
Chamber pressures have plateaued.
Spacecraft design saw crucial electronics shielded within a thick titanium vault, and rather than a plutonium power source, Juno would rely on solar panels. The Sun's intensity at Jupiter is roughly 5% of what it is at Earth, so the panels are huge. A shortage in stocks of plutonium-238 led to the change in power sources. Juno followed a looping orbit that took it beyond Mars before swooping back to Earth for a gravitational boost that added 14,000 kilometers per hour to its velocity, sending it on to Jupiter. Juno approached Jupiter on a path that took it above the planet's north pole. It was destined for a north-south orbit. This would see it pass beneath the severest sections of the planet's radiation belts that extend out from Jupiter's equator. 4 days before its closest approach, Mission Control sent a command that initiated the craft's autopilot. On July the 4th, 2016, Juno began an engine burn that would insert it into a 53-day orbit. 48 minutes later, Mission Control at JPL received tones verifying that Juno had started its deceleration maneuver. It was a tense 35-minute wait from the system's engineers before confirmation came through that Juno had performed exactly as intended. For the Juno scientists and engineers, it was a relief that things were going to plan.
Roger, don't move, Juno.
Juno is equipped with a suite of instruments capable of penetrating Jupiter's thick cloud. The polar orbit allows Juno to compile a three-dimensional map of the upper atmosphere, building a picture of the entire planet as it rotates. The images of Jupiter from this new perspective appeared to come from a different planet. Researchers were stunned. It was planned that Juno would only make 2 53-day orbits and then change to a series of 14-day orbits that would speed up the sampling rate. The spacecraft's main engine is fueled by hydrazine and nitrogen tetroxide, which ignite spontaneously when mixed. The propellant and oxidizer are forced out by a bladder of expanding helium. As Juno was finishing its second orbit, the helium valves were not responding correctly, so it was decided to maintain the original orbit. A mission extension has been granted to allow for the longer orbits Juno continues to follow. Within a day of the helium valve problem, Juno went into safe mode. All instruments went offline and data was lost. It appeared to be similar to the difficulties experienced by Galileo, but engineers traced the issue to a data transfer problem from one specific instrument, and the spacecraft remains healthy. Jupiter's axis is tilted at only 3 degrees, making even an oblique view of the poles near impossible until Juno arrived. When viewed in the infrared, researchers saw a complex arrangement of storms at both the poles. At the North Pole, a central vortex is surrounded by 8 anticyclones. At the South Pole, 5 anticyclones surround the central storm. Scientists do not understand why the storms, all rotating in the same direction, do not obliterate each other. On its 7th close pass of Jupiter, Juno flew directly over the giant red spot. Its microwave radiometer was able to map the heat distributions at varying levels down to 350 kilometers. The red spot is a giant storm, and Juno was able to see much higher temperatures at the deepest levels they could penetrate. With no geographic features, as on Earth, there is nothing on Jupiter against which storms can dissipate. The Great Red Spot remains firmly 22 degrees below the equator, yet it appears to have drifted around the planet at least 10 times since reliable observations began. Jupiter's magnetosphere is huge. It traps charged particles in bands stretching out to vast distances. This gives sensitive electronics on orbiting spacecraft like Juno big problems. It was assumed that Jupiter's magnetosphere was generated, like Earth's, by dynamo action, the convective movement of an electrically conductive fluid deep within. So far, results from Juno suggest that this is not the case. The lumpy nature of Jupiter's magnetic field points to an atmospheric source. The giant auroras at the poles also seem to come from a different mechanism than here on Earth. By focusing on the composition of the gas giant, researchers are hoping to gather clues about conditions at the formation of the solar system. While the Earth has been continuously changed by tectonic forces, it is thought that Jupiter remains very similar in composition to the cloud of gas and dust from which the solar system was formed. At the end of its mission, Juno will be sent on a collision course with Jupiter to avoid any possible contamination of the delicate moons. The next mission to the Jovian system will focus on Europa, as the most likely place after Earth to harbor some form of life. Known as Europa Clipper, it's scheduled to launch in 2022. Like Juno, it will be solar-powered, and its elliptical orbit of Jupiter will see it fly over Europa every 2 weeks. Early concepts for the mission called for the inclusion of a lander, but this idea was soon rejected as premature because more needs to be learned about the surface of the icy moon. Though Europa's ice crust is thought to be at least 19 kilometers thick, accurate measurements need to be made. If thin areas can be found, then future missions may be able to access the ocean that lies beneath. Concepts for under-ice explorers are in development, and we can expect other missions to focus on other moons. As the largest planet, Jupiter's influence on the rest of the solar system is profound. It has more than twice the mass of every other planet combined. All other planets' orbits are affected by Jupiter's gravitation. There is still much to learn about Jupiter. The International Space Station is a laboratory that orbits the Earth once every 90 minutes. It's the most expensive single project ever constructed. Jointly owned and operated by the United States, Russia, Europe, Japan, and Canada, the ISS is a triumph of international collaboration. But it didn't start that way, and during its planning phase, it came close to being dumped.
Tonight, I am directing NASA to develop a permanently manned space station and to do it within a decade.
It was 1984, toward the end of the Cold War. when President Ronald Reagan unveiled his plan before the Congress. It was soon called Space Station Freedom, but details were sketchy and plans kept changing. NASA saw a space station as their next logical step. The Space Shuttle had been designed with on-orbit construction as one of its primary functions. On a cold morning in January 1986, the Space Shuttle Challenger was being prepared for its 10th flight.
And liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Challenger, go and throttle up. Challenger, go and throttle up.
All 7 astronauts were killed, and the shuttle program was suspended. Just 1 month later, cosmonauts began occupation of Mir, the new Soviet space station. The Soviet Union had a long-standing interest in extended duration space flights with its Salyut space stations. And with Mir, the Russians were gaining valuable experience in microgravity research and on-orbit construction. As the 80s progressed, Mir expanded using modular fabrication techniques. They began experimentation with automated docking systems. New modules were delivered by the Proton launcher with the Progress cargo ship used for resupply. NASA's shuttle fleet remained grounded, while an exhaustive inquiry was conducted, and Space Station Freedom was stuck on the drawing board. In 1989, discontent in Poland spread across the Eastern Bloc, leading to the fall of the wall that had divided Germany. 2 years later, the Soviet Union itself was dissolved, followed by social and economic turmoil. Moscow was now the capital of the Russian Federation, a one-party democracy. The Mir crew EO-10 arrived at the space station as Soviet citizens and would return to the ground as Russians. The country's new space agency, Roscosmos, had had its budget slashed by 80%, and there was no money to launch 2 newly completed modules. In 1988, NASA had resumed shuttle flights. But with the fall of the Soviet Union, interest among US politicians in Space Station Freedom was at an all-time low.
Roger, roll, Discovery.
NASA now began working with Roscosmos. In the Shuttle Mir program, the Russians would benefit from an injection of badly needed funds, and the Americans would gain expertise in long-duration spaceflight. Astronauts learned Russian and began riding to orbit in the Soyuz. Cosmonauts learned English. During the program, 10 cosmonauts flew on the Space Shuttle, and 8 Americans served as crew members aboard Mir, with the shuttle docking with the Russian space station 9 times. Roscosmos had begun work on a replacement Mir 2 project, completing the functional cargo block and the DOS-8 habitation module. But lack of funding forced the agency to shelve the plan. NASA convinced the cash-strapped Russian Federation to come in on their project. Europe, Japan, and Canada were also involved in what was now called the International Space Station. The functional cargo block was renamed Zarya and became the first piece of the International Space Station delivered to orbit in November 1998. Zarya was launched from Kazakhstan with an orbital inclination of around 50 degrees. This set the orbit for the International Space Station. The Space Shuttle would deliver the bulk of the modules from here on. NASA knew that this orbit would give the shuttle problems. Launched from Florida, the shuttle usually orbited at 30 degrees. To reach the steeper inclination with any meaningful payload, the shuttle needed more power, or it had to lose weight. A redesign of the cargo bay delivered some weight savings, but the construction missions could only be achieved with a new external tank made from a new lightweight alloy.
We have a go for main engine start. We have main engine start. 4, 3, 2, 1. We have booster ignition and liftoff of the Space Shuttle Endeavour with the first American element of...
2 weeks after the launch of Zarya, the Space Shuttle Endeavour lifted the Unity node to orbit.
Houston's now controlling. Endeavour's rolling on a course heading northeast from the Kennedy Space Center toward a 240-mile-high rendezvous with the Zarya control module.
In preparation, the crew connected the Unity node to the shuttle's airlock, and using the shuttle's robotic arm, they united the two modules. The crew entered the space station for the first time and stowed equipment, but no one would take up residence just yet. Construction work had just started. It was 18 months before the arrival of the next module, Zvezda, the Russian habitation module. It docked automatically with the Zarya module. In October 2000, the Space Shuttle Discovery arrived with more pieces. During 4 spacewalks, the crew installed a structural truss and communications equipment. Finally, in November 2000, the first crew, Expedition 1, launched from Baikonur. Cosmonaut Yuri Gidzenko was commander of the Soyuz spacecraft. Astronaut Bill Shepard was the commander of the team once they were on the International Space Station, and Sergei Krikalev, the most experienced member of the crew, was flight engineer. Much of the crew's daily activity was devoted to the unpacking and installation of equipment. There are always problems that need to be solved and maintenance to be carried out. In microgravity, muscles lose tone. One of the first pieces of equipment to be set up was an exercise bike. Every crew member is required to do 2.5 hours of cardio exertion every day. Unlike later missions, Expedition 1 carried out very little scientific research. At this stage, the station's primary laboratory module was still on the ground. But that would soon change. The crew of the space shuttle Atlantis delivered the laboratory module called Destiny. It was a radical increase in capability for the space station. The laboratory is equipped with 13 international standard payload racks that can house a variety of different experiment modules, but at this stage they were empty. With the Destiny module and a new, much larger solar array, the International Space Station was taking shape. A precisely organized launch schedule was unfolding, and it was expected that the space station would be complete by 2006. In November of 2002, the Space Shuttle Endeavour took off, carrying the Expedition 6 crew, plus a new piece of the space station's superstructure and 2 tons of supplies. Returning to the ground, no one realized that it would be the last time a cosmonaut would fly on the shuttle, and that construction work on the ISS would be suspended for more than 2 years.
Columbia, Houston, comm check.
When the Space Shuttle Columbia broke up during re-entry to the Earth's atmosphere, all remaining shuttles were grounded.
Columbia, Houston, UHF, comm check.
81 seconds after launch, foam insulation separating from the external tank had damaged the left wing, and from that point, Columbia was doomed. The investigation board had no confidence that the entire space shuttle fleet could be safely operated for more than a few years, calling the shuttle an aging spacecraft. With shuttle flights suspended, construction work on the International Space Station stopped. Replacement crews were cut to 2 members. The Russian Progress freighter was the only method of delivering supplies to the ISS, and all crew rotations used the Soyuz spacecraft.
Принято 30 секунд, на борту порядок.
What started out as America's space station freedom was now completely reliant upon Russian technology. It would be more than 3 years before construction work on the space station recommenced. In 2004, US President George Bush made a speech to an assembled group of NASA administrators.
Our first goal is to complete the International Space Station by 2010. In 2010, the Space Shuttle, after nearly 30 years of duty, will be retired from service.
The Space Shuttle would be restricted to work on the International Space Station, where the crew could await rescue if their craft sustained damage. Scientific work was cut to a minimum, with the small crews preoccupied with station maintenance. Fabrication work on the modules continued on the ground. The Space Shuttle Discovery made the return to flight mission in 2005. Before docking with the International Space Station, it performed the rendezvous pitch maneuver, allowing the ISS crew to inspect the craft for damage. It delivered supplies and equipment and returned safely to the ground. Atlantis arrived 14 months later, and after a break of almost 4 years, construction work began again. In what became known to NASA astronauts as the Wall of EVA, that's extravehicular activity, it took 14 more shuttle assembly flights to bring the ISS to its current configuration. If just one of the installation's spacewalks was to fail, it could threaten the entire project. The schedule was relentless because the shuttle's days were numbered. Training for these assembly missions was intense. NASA's neutral buoyancy laboratory was rigged with a mock-up of the ISS, so astronauts could experience something akin to weightlessness while they practiced. In July 2011, Atlantis flew to the ISS on what was the final flight of the shuttle fleet. The International Space Station was essentially complete, although it continues to be reconfigured and new pieces can still be added. Its 16 pressurized modules have a volume equivalent to a 5-room house, including laboratories, storage spaces, and habitation areas. Power comes from 8 solar array wings, which track the sun. When the ISS enters the Earth's shadow, the solar wings enter night glider mode, where they are angled edge-on to the orbital direction. Though the ISS orbits 400 kilometers above the Earth's surface, there is enough thin atmosphere at that height to present drag. Night glider mode reduces this drag and minimizes orbital decay. Supplies of water, oxygen, food, and equipment are regularly delivered by unmanned cargo craft. Most frequent of these has been the Russian Progress, which is similar in appearance to the Soyuz. It docks by itself using the automated Kurs system. It can also be docked manually if the need should arise. Like the Soyuz capsule, the Progress freighter will remain docked long-term. As well as delivering supplies, it can boost the station's orbit, or it can transfer fuel for the station's thrusters. Ultimately, filled with garbage, it undocks to burn up in the atmosphere. The Japanese space agency, JAXA, currently operates the largest cargo craft that still visits the ISS. To dock with the space station, it approaches in stages, until it's close enough to be grabbed by the robotic arm and connected to one of the berths on the Harmony node. It has a pressurized zone that can be unloaded by hand, and there's an unpressurized area, accessed by the robotic arm, for cargo to be stored on pallets outside. With the demise of the Space Shuttle, NASA has turned to the private sector to fulfill its resupply commitments. The Cygnus freighter first visited the ISS in 2014. The SpaceX Dragon cargo craft first delivered supplies to the ISS in 2012. It is different from the other cargo craft in that it can return significant loads back to the ground. Experimental materials from the ISS can be in an Earth-based laboratory within 2 days of leaving low Earth orbit. SpaceX is developing a Dragon capable of carrying astronauts to low Earth orbit. The business of the International Space Station is research. The study of fluid dynamics and materials science in a microgravity environment simply cannot be done on the ground, and the orbiting platform is the perfect place for Earth observation, meteorological studies, and astronomy. The study of plant development in microgravity is of great interest. One of the major areas of study is into the effects of prolonged weightlessness on the human body. Without the resistance provided by gravity, muscles and bone deteriorate. This is partially offset by regular exercise. The ISS is equipped with a treadmill, a cycle ergometer, and a resistive exercise device. All are shock-mounted so as not to pass vibration across the station. The loss of bone mass shows up as raised calcium levels in the blood. Blood samples are taken regularly and stored at low temperature for later analysis. The extra calcium can lead to kidney stones. NASA and JAXA are cooperating in the study of an agent that can prevent these effects. Most astronauts on long-term missions complain about deterioration in their vision, which can persist for years after a flight. Distinct changes to the eye have been detected, and ultrasound examinations of the eyes are done regularly. Astronauts and cosmonauts are totally reliant upon the technology of the ISS, and it needs regular maintenance. In August 2018, a small but steady drop in air pressure was noticed. It was traced to the Soyuz MS-9 capsule. A 2-millimeter hole appeared to have been deliberately drilled, and nasty rumors about sabotage began to spread. Cosmonaut Sergei Prokopyev made a recording from the Soyuz to show the repairs and to quash stories about poor morale on the space station.
As you see, everything is calm. We're living in harmony as always, and all the experiments are going to plan.
Later, it was decided that a spacewalk to cut away some of the external insulation from the Soyuz above the hull might deliver more clues about how the hull could have been made. Because the Soyuz capsule is not designed for external maintenance and lacks handrails, it was a challenging job for the cosmonauts. It was difficult slicing through the 8 layers of the thermal blanket used to stabilize internal temperatures on the spacecraft. From the inside, it appeared that the hole had been repaired with glue, which gave out after the Soyuz had docked with the ISS. It was thought that analysis of the glue would shed more light on the mystery. Because the hole was in the habitation module, it was no threat to the craft's safe return. The blanket, which was left in a mess, is also not required during re-entry.
Now I see it, Moscow.
Russian cosmonaut Sergei Prokopyev, European astronaut Alexander Gerst, and American astronaut Serena Agnon-Chancellor had flown up on this spacecraft and would be returning home on it.
Cut the visible portion.
When maintenance or repair work has to be done outside the ISS on NASA, ESA or JAXA modules, the crew members with the required expertise have training in the use of the American spacesuit, known as the EMU. Some crew members have training on the EMU and the Russian Orlan spacesuit. Those with experience in both say that the American suit is more flexible and comfortable, yet it is very complex and takes a very long time to put on. By contrast, the Russian suit is simple to put on and is designed to be easily serviced by cosmonauts. Even the smallest equipment malfunction can be life-threatening. When ESA astronaut Luca Parmitano was installing cables outside the ISS, water started leaking into his helmet.
I feel a lot of water on the back of my head, but I don't think it's leaked from my back.
Are you sweating? You working hard?
I am sweating, but it feels like a lot of water.
Mission Control called him back inside, but by the time he had reached the airlock, he couldn't see and he couldn't hear. His colleagues quickly got him inside and removed his helmet, along with more than a liter of water. Later, the empty suit was powered up and the fault was obvious. The water was leaking from the suit's cooling system. A report blamed Mission Control, who assumed that the water was coming from the in-suit drinking water bag. A crew will typically stay in orbit for around 6 months. The arrival of a new crew means that for 3 other crew members, their stay is coming to an end. They board the same Soyuz craft in which they traveled to orbit for the return to the surface. Undocking of the capsule is precisely timed. It separates initially by the spring mechanism in the docking interface. Only at a safe distance from the ISS will the Soyuz make the first of its separation burns to avoid contaminating the space station. At a point in the orbit opposite to their intended landing area, the retroburn happens, slowing the craft for its descent into the atmosphere. This burn is precisely timed and lasts 4 minutes and 45 seconds. At this stage, the descent capsule is still attached to the habitation and instrument modules. In Kazakhstan, a fleet of ground vehicles are heading for the landing zone. Medical teams and recovery personnel from Roscosmos, NASA and ESA are also in the air. Explosive bolts fire to separate the 3 parts of the Soyuz. During the heat of re-entry, the crew are out of radio contact with the ground. In the upper atmosphere, the drogue chute deploys, further slowing the capsule. And then the main chute. On the ground, the crew are lifted from the capsule. They're experiencing gravity for the first time in months, and it will take them months to return to normal. They are carried through the snow and will soon return to their homes. The ringed planet Saturn. More than 100 times the mass of Earth. Its metallic core lies beneath 80,000 kilometers of liquid hydrogen and helium. It's called a gas giant. Saturn is orbited by at least 62 moons, each unique, some with complex and dynamic environments. Our only detailed examination of the Saturnian system ended in 2017, when the Cassini probe was intentionally crashed into the planet's dense atmosphere to guard against accidental contamination of the moons. from Earth, Saturn's rings are visible, but not in any detail. They were thought to be solid until mathematical analysis suggested they were orbiting particles. But how did they get there? And why was Saturn alone in having rings? In the early days of space research, Saturn was just too far away. Conventional rockets could only just reach Mars. In 1964, NASA realized that a space probe launched in 1977 could take advantage of a rare alignment of the outer planets to fly past all the gas giants. Using gravitational assistance from the planets, it would just be possible with the technology of the day. An ambitious new mission began to take shape. It was dubbed the Grand Tour. Two probes that were far in advance of anything yet attempted would be part of the Mariner series. Because no spacecraft had been sent beyond Mars, mission planners felt it would be wise to send two rudimentary advanced probes to Jupiter and Saturn to test the deep space environment. Researchers didn't know if it was even possible to cross the asteroid belt between Mars and Jupiter. In 1972, Pioneer 10 was launched towards Jupiter, and the following year, a twin, Pioneer 11, was sent to Saturn. Both craft passed by Jupiter and discovered that the electron radiation there was 10,000 times as strong as at Earth. This was a surprise to engineers at NASA, who had to modify the more sophisticated craft they were preparing for the Grand Tour. The probes, being built at NASA's Jet Propulsion Laboratory, were part of a program known as Mariner Jupiter-Saturn, but this was soon changed to the Voyager program. They were launched 16 days apart in late 1977, while Pioneer 10 was heading toward interstellar space, and Pioneer 11 was still 2 years away from Saturn. In 1979, as Pioneer 11 approached the ringed planet, it began sending back pictures far clearer than anything seen before. A new ring, the F ring, was observed for the first time. The craft flew by Saturn, passing beneath the rings. Mission planners were uncertain how broadly the ring particles spread. If there was a threat to the spacecraft, they were prepared to sacrifice Pioneer 11 to get a clear idea of the environment they would encounter with the following Voyager craft. The probe passed the rings safely and continued beyond Saturn into interstellar space. NASA received its last communication from the probe on the 24th of November 1995. The following Voyager 1 and 2 probes were very robust, designed to survive for a very long journey and with far greater technical capacity than the Pioneers. In late 1980, Voyager 1 approached Saturn. Although its high-resolution polarimeter had failed, it was still able to see a new ring called the G ring, orbiting 100,000 kilometers above Saturn's cloud tops. For the first time, researchers could see how the rings moved. Uneven features within the rings were called spokes. They are transient and are thought to be particles lifted by an electrostatic charge. After such a long preparation, information was now coming into JPL at such a rapid rate that the planetary scientists were overwhelmed. Saturn's moons were of great interest. Voyager 1's path had been chosen because it would take it close to Triton, the solar system's second largest moon, and the only one to hold an atmosphere. But the images were disappointing because the thick atmosphere of methane and nitrogen was impenetrable. Voyager 1 now looped up above the solar system on a trajectory that would take it to interstellar space. As it looked back at Saturn, it captured one last image from a unique angle. It was almost 10 months before Voyager 2 neared Saturn. Its different path meant that it could continue on to Uranus and then to Neptune. Its high-definition camera was still working, and planetary researchers were expecting detailed pictures of the rings. They were not disappointed. The varying densities and spacing within the rings was more complex than anyone had expected. The rings are named for letters of the alphabet in the order that they were discovered. It became apparent that the rings had changed in the time since Voyager 1 had seen them. Though they stretch from 7,000 to 80,000 kilometers above Saturn's equator, their thickness is on average just 30 meters. The spacecraft also returned pictures of the moon Enceladus. Its cracked, uncratered surface was made of ice, below which is an ocean. Ultimately, Voyager 2 left Saturn. Unable to go into orbit, it sped on toward Uranus. It would be 23 years before another probe visited.
And liftoff of the Cassini spacecraft on a 30-mile trek to Saturn.
Launched in 1997, Cassini was a collaboration between NASA, the European Space Agency, and the Italian Space Agency. It would take more than 6 years to reach Saturn. Cassini was the biggest, most complex interplanetary spacecraft yet devised. Its 12 different instruments each had a dedicated team of research specialists on Earth to interpret the data it sent back. Its high-gain antenna was used for high-speed data relay back to Earth, but in what's called a ram maneuver, it was sometimes used as a shield to protect the spacecraft from debris impact, especially when crossing the plane of Saturn's rings. On the 1st of July 2004, it fired its engine to go into orbit around Saturn. It was designed not to fail. Beside its main engine was a backup, in case the primary engine did fail. It had 16 monopropellant thrusters, 8 prime, and 8 more, also as backups. In mission control at the Jet Propulsion Laboratory, the engineers could not know what was going on. The time delay and Cassini's disappearance behind Saturn meant that much of the telemetry was recorded for later replay back to Earth. The engine burn lasted for 106 minutes. Cassini was the first probe to employ a solid-state recorder, unlike the earlier Voyager craft that registered data on a mechanical tape recorder. Cassini's first orbit followed a highly elliptical path that would take it out past the moon Triton. This was important for 2 reasons. Its gravity would be necessary in modifying Cassini's course, so Saturn and its other moons could be observed from different perspectives. Secondly, Triton, with its dense atmosphere, was targeted as an area of major interest for the Cassini team. The European Space Agency had built a small craft called Huygens, attached to the side of Cassini. On its second approach to Triton, the Huygens probe was released. It was equipped with a heat shield, a parachute, and enough battery power to last for several weeks. Over a 20-day period, Huygens drifted for 4 million kilometers. It would transmit data back to the orbiting Cassini, which would later relay it to Earth. 3 days after separation, Cassini made a course correction that would prevent it colliding with Titan. As Huygens reached Titan's atmosphere, Cassini was coming around for its third close approach of the Moon, ready to receive signals from the lander. While it drifted to the surface of Titan, Huygens sampled the atmosphere and recorded images of the landscape. Pictures from beneath the clouds revealed low hills and channels cut by flowing liquid. There were few impact craters, and those that existed were heavily eroded. It was the first landing on a body in the outer solar system. Images from the surface showed weathered rocks made of water ice. What surprised everybody was that Titan is a geologically active world, where liquid ethane and methane, rather than water, have carved the features. As Cassini continued looping out around Titan, it used radar to map the Moon's surface, confirming the widespread distribution of hydrocarbon lakes. The probe discovered that rain fell on Titan, but it was a mixture of liquid ethane and methane. The Moon has weather and other erosive forces similar to Earth, but the chemistry is radically different. The small moon Enceladus drew attention to itself as the whitest, most reflective body in the solar system. Its surface shows cratering in the north, but the south has giant cracks known as tiger stripes. On Cassini's first loop past Enceladus, the magnetometer team noticed an odd deflection of Saturn's magnetic field, as though the small moon had an atmosphere. During its second pass, the team noticed the same phenomenon. They asked for the next traverse of Enceladus to pass much closer, so Cassini's course was modified to fly just 175 kilometers above the icy moon. The probe passed through a plume of water vapor emanating from the tiger stripes. It contained common salt. In all, Cassini made 24 swoops past Enceladus, with the closest approach flying just 25 kilometers above the surface. Each one of the probe's instruments gathered different evidence about the jets of water expelled through the cracks in the moon's south. On Mars, rovers have been combing the surface looking for traces of life, but Enceladus was flaunting remarkable signs. Gravitational analysis revealed a liquid ocean beneath the ice, and infrared detectors saw heat emanating from the cracks. As well as salt, the science team discovered traces of silica that can only dissolve in hot water. Hydrogen and organic compounds were also detected.
We know from Cassini that Enceladus has a global ocean, so you have water. We also know that there are organics coming out because they've been directly measured, both in the gas and in the particles. We also know there's a source of energy. The South Pole was hotter than the rest of Enceladus. And then we found evidence that deep inside, there are hydrothermal vents on the seafloor of Enceladus. So these hydrothermal vents would supply the heat and the nutrients that could possibly support life.
With a diameter of 500 kilometers, Enceladus is just too small to sustain a hot core via radioactive decay. Gravitational squeezing by Saturn explains some of the heating, but the source of the high temperatures detected remains a mystery.
But not only is there liquid water underneath the surface, but there's organic material, there's a heat source. And you know, when people get excited about the potential for life elsewhere in the solar system, there are four things that you need. You need a heat source, You need liquid water, you need organic material, and you need those three things to be stable over some period of time so that life could potentially form. At Enceladus, we've got three. We're not sure about the stability over time yet.
In the Earth's deep oceans, hydrothermal vents provide the warmth and nutrition to support life. They may even have been important for the origins of life. Planetary biologists are speculating that the environment in the oceans of Enceladus may be the most likely place in the solar system to find some sort of extraterrestrial life. It took a while for Cassini to be in a position where backlighting from the sun allowed the imaging team to capture pictures of the plumes. Using a similar technique, the imaging team took this picture with Saturn directly between Cassini and the Sun. It reveals Saturn's E-ring, the hazy outermost ring that is usually very difficult to see. The E-ring is a result of the plumes from Enceladus and is constantly replenished by the saltwater eruptions. Saying that Saturn has 62 moons is misleading. Each particle within the ring system could be regarded as a moon. There are the inner large moons and the outer large moons. There are the shepherds that shape the rings. There are co-orbitals that exchange orbits. And there are even moons that orbit other moons. All are unique. During the Voyager missions, interest in the moons came as something of an afterthought, but for Cassini, close examination of the moons was planned from the beginning. Iapetus orbits Saturn beyond Triton. It was first observed in 1671 by Giovanni Cassini. He could see it as a dot of light to the west of Saturn, but could not see it when it should have been to the east. Iapetus has one bright face and one dark one. Because the moon is tidally locked to Saturn, it is always the dark face that leads as it orbits. One theory suggests that it sweeps up debris that spews from Phoebe, a more distant moon. Another feature of Iapetus has scientists baffled. A ridge along the equator stretches more than halfway around the moon. It's twice as high as Earth's tallest mountain. With Iapetus being just 1,500 kilometers across, the ridge gives Iapetus the appearance of a walnut. Very accurately directed bursts from Cassini's main engine allowed mission engineers to modify the probe's looping orbits so mission specialists could focus on various moons, different areas of the ring system, or different parts of Saturn itself. With gravitational assistance from the moons, particularly Titan, mission control were able to conserve fuel. The Cassini probe performed so well it received 2 mission extensions, but the fuel could not last forever. Planners had scheduled the most hazardous part of Cassini's mission for its final year at Saturn. Late in 2016, Cassini began a series of polar orbits that would take it close to the outer edge of the rings. In what mission specialists called grazing on the rings, the craft's mass spectrometer and its cosmic dust analyzer would sample particles and gases as it crossed the ring plane. In orbit 251, its first pass above Saturn's North Pole, it recorded the peculiar hexagonal storm that was first hinted at by the Voyagers. The storm, more than twice the diameter of Earth, maintains its hexagonal shape, but its color changed with the advance of summer. At its center is a cyclone, shown here in false color, with red indicating lower cloud and green higher cloud. Winds at its edge blow at 540 kilometers per hour. One part of Cassini's dual-technique magnetometer had stopped working early in the mission. Without it, the craft had to do roll maneuvers from time to time to calibrate the instrument. The spacecraft would make 20 ring-grazing orbits, with the work of its instruments mapped out to the second. As the Sun was almost directly behind the rings, Cassini looked for dust clouds. Something is reducing ring particles to fine powder. Cassini made a number of radio occultation observations. With the rings between the spacecraft and Earth, 3 radio signals of differing wavelengths were transmitted simultaneously, allowing the radio science team to build a profile of the ring particles. This false color image of the A ring, the outermost of the large bright rings, shows red for particles larger than 5 centimeters across. Green denotes particles smaller than 5 centimeters, with blue for particles smaller than 1 centimeter. The complex gravitational interaction between Saturn, its rings, and its moons leads to gaps in very particular places. Before Cassini arrived, only 18 moons were known. That number has grown to 62. Prometheus acts as a shepherding moon, limiting the inner edge of Saturn's F ring. Along with Pandora, which orbits outside the F ring, the 2 moons keep the ring narrowly confined. In April 2017, Cassini's orbit was changed for the final phase of its mission. The probe would now loop inside the rings. Though it would ultimately mean burning up in Saturn's atmosphere, the information gathered from such close proximity to Saturn and its rings would give a fuller picture of the gas giant. It was decided that intentionally destroying Cassini was preferable to letting it drift without fuel, possibly contaminating one of the moons. Cassini's sensors began picking up a stream of ring particles raining down upon Saturn. A continuous shower of ice and dust particles are dragged toward the planet's equator by gravity, or at higher latitudes, charged ring particles spiral in along magnetic field lines. Every second, 10,000 kilograms of ring rain falls to the surface. At this rate, the rings will be completely gone in 100 million years. Researchers were surprised to discover an electric current flowing between the inner D ring and the upper atmosphere. Toward the end of Cassini's close passes of Saturn, the spacecraft began catching the upper edge of the atmosphere. All information had been retrieved from the recorders. Data now was transmitted directly back to Earth, but it relied on the spacecraft's thrusters to stop Cassini from tumbling, keeping its high-gain antenna pointed accurately. The probe's final work was sampling the atmosphere and measuring the offset of Saturn's magnetic axis.
This is PCS-1. We just had transition to high rate mode.
In mission control, there was no more control. The engineers could just monitor the signals sent from Saturn 84 minutes previously.
The signal from the spacecraft is gone, and within the next 45 seconds, so will be the spacecraft.
It will take years to process the data gained from Cassini. As yet, there are no future missions to Saturn scheduled. Mars, our planetary neighbor. It's very cold and dry, and its weak gravity only holds a thin atmosphere. As probes started to visit the red planet, we gained a more accurate view of the surface, and scientists began to wonder. Mars had once been much warmer. It had rivers, and in its early years might have sustained life. A succession of new techniques have been deployed trying to unlock the secrets of the red planet. And while our knowledge of the Martian geology, its atmosphere and its weather has grown immensely, each new mission to Mars raises more questions than it answers. We still don't know if Mars has, at some time, been a home to life. In 1877, astronomer Giovanni Schiaparelli made what he thought was the most accurate map of Mars yet drawn. On it, he showed canals. In the early 20th century, American astronomer Percival Lowell was convinced the canals were signs of a civilization existing on the red planet. So began the search for life on Mars. In 1962, the Soviet Union sent the first probe, the Mars M1, on a flyby mission. It was an audacious project, and it failed. The first of many failures by both the Soviet Union and the United States. Cold War rivalry provided the motivation for these early missions. In 1971, NASA sent Mariner 9 to Mars. It was the first probe to orbit another planet, but scientists discovered that Mars was enveloped in a planetary dust storm. On-orbit photography revealed little more than a red cloud. Soon, Mariner 9 was joined by two Soviet orbiters, both equipped with landers. The Mars 2 lander crashed, but the Mars 3 lander made it to the surface intact. It returned one garbled image and then stopped functioning. Mars now had 3 orbiting spacecraft, all looking at a dusty, featureless planet. The 2 Soviet probes were identical, but the American probe had one key design difference. While the Soviet orbiters began photographing the planet following predetermined schedules, NASA were able to command Mariner 9 to wait, in hope that the dust would eventually settle. It took months for the atmosphere to clear, but when it did, Mariner 9 saw 3 craters protruding above the dust. They were the tops of giant volcanoes on what was called the Tharsis Plateau. Soon more complex geological features began to emerge. In places, the surface was cratered, suggesting the tectonic forces that constantly renew the Earth's surface were absent on Mars. Volcanic activity that built the solar system's largest volcanoes had stopped billions of years ago. This enabled NASA scientists to compile an accurate global map of Mars and to decide upon landing sites for the Viking probes that followed in 1976. Viking 1 and 2 were identical orbiters, with landers that both made successful landings on the surface. Both returned pictures of the Martian landscape. The primary objective of the Viking program was to find signatures of life. But researchers now feel the 3 experiments tasked with carrying out the analysis had limitations. As researchers on Earth began looking for traces of life in extreme environments, they began to rethink where life on Mars might survive. Yet the consensus at the time was that Mars was sterile, and the idea of life on Mars died. After a 20-year hiatus in Mars research, Mars Global Surveyor went into orbit in 1996. The pictures it relayed back were clearer than anything yet seen from the red planet. Although most Mars orbiters had been tasked with mapping the planet's surface, this was different. The high-resolution images that the Mars Global Surveyor sent back revealed rivers and even river deltas, but the occasional impact crater suggested that nothing has flowed in these systems for billions of years. In July 1997, another probe arrived. The Mars Pathfinder was one of a new breed of missions being pushed by NASA's new administrator under the guiding philosophy of faster, better, cheaper. The idea was to cut development times, cut budgets, and although the risk of failure would rise, the reduced price tag could mean more missions. Pathfinder would land a small rover on the surface. To do this, it used radically new airbag technology. The technique drew more from automotive safety systems than from previous space missions. The landing site, in Mars' northern hemisphere known as Ares Vallis, is one of the planet's rockiest areas. Yet it was thought to be a safe area to land. The broad array of different rock types are believed to have been deposited during an ancient flood. The new landing technique worked perfectly and served as a proof of concept that would be used on future missions. Pathfinder consisted of a base station equipped with 3 solar panels that unfolded like petals. There were sensors to measure atmospheric pressure, air temperature, and wind speed, as well as a transmitter to communicate with Earth. In addition, Pathfinder acted as a base station for the Sojourner rover that explored the surrounding area. Sojourner was fitted with cameras and an alpha particle X-ray spectrometer. It was the first mission to have its own website. The rover returned thousands of images and important detail about the atmosphere and geology, and its popularity guaranteed more Mars missions. On the morning of April 7th, 2001, another Mars orbiter was launched. Mars Odyssey was equipped with 3 primary instruments, and it had the ability to act as a relay satellite between future surface missions to the Red Planet and Earth. On its arrival at Mars, it used a new technique to go into orbit. After firing a relatively brief pulse of its engine, Mars Odyssey went into a highly elliptical orbit that, at its closest approach, had it skimming the planet's thin upper atmosphere. Called aerobraking, this technique allowed the craft to circularize its orbit over a period of 3 months, and it saved around 200 kilograms of fuel. The probe is still in operation today, breaking all records as the longest-serving Mars mission. In December 2003, a new player arrived at Mars. The European Space Agency, using a Russian launcher, had sent Mars Express, its first planetary explorer. It was equipped with a lander known as Beagle. Though all contact was lost with the lander, Mars Express continues to return valuable data. The mission has been granted several extensions, the latest till 2020. Equipped with a high-resolution stereo camera, the probe returned unique 3D views of the planet's surface. The orbiter determined that the polar ice caps contain a blend of frozen CO2 and water ice. In the atmosphere, Mars Express detected first methane and then ammonia. Both gases deteriorate rapidly in sunlight, so there must be sources on Mars continually producing them. Methane and ammonia can rarely be made inorganically, but they're generally associated with life. 1 month after Mars Express went into orbit, a NASA lander arrived at Mars, followed 3 weeks later by a second identical craft. They were the Mars exploration rovers called Spirit and Opportunity. Spirit, the first to land, was targeted at the Gusev crater. Opportunity would land at the Meridiani planum on the opposite side of Mars. Though they were much heavier than their Pathfinder predecessor, they used the same bounce landing technique. Both landings were successful and on target. After the craft had righted itself, it detached from the lander and began autonomously unfolding its solar panels and camera mast. While this was happening, the team back at the Jet Propulsion Laboratory waited. Signals confirming the craft's safe arrival took 15 minutes to travel back to Earth. Many of these people had invested years of their lives in this project, and the real mission had only just commenced. Both rovers were designed to operate for 90 Mars days. A solar day on Mars is about 40 minutes longer than an Earth day. And to avoid confusion, the science team operating the rovers refer to a Martian day as a sol. Mission designers, knowing about the dust storms on Mars, felt that the solar panels on the two rovers would eventually be blocked with dirt and stop functioning. But it became clear that the winds on Mars were clearing the panels. Soon, NASA announced that Opportunity had found evidence confirming liquid water had once flowed on Mars. There were pictures from the Meridiani planum of stratified patterns in the rock suggesting sedimentation. The distribution of chlorine and bromine at the site were clues to the areas past as the shore of a salty sea. In April 2004, NASA announced it would extend the rover's missions from 3 to 8 months. It would be the first of many such mission extensions. The rovers were equipped with an abrasion tool to grind away a portion of a rock's surface for a more detailed, uncontaminated analysis of geological samples. This was first done by Spirit at a rock named Adirondack at Gusev crater. It was a first in planetary geology. Researchers agonized before using the tool because of the drain it makes on the rover's energy budget. The rock was made of olivine, pyroxene, and magnetite, making it very similar to volcanic basalt on Earth. When Spirit's right front wheel stopped working, engineers used a duplicate rover to devise a reversing technique that enabled the rover to drag its frozen wheel. This left a furrow behind in the soil, which presented a new area of research for the science team. White or yellow deposits seen within the furrow were various types of salts that only form in the presence of hot water. On Earth, hot water provides an environment in which microbes can thrive. Spirit limped on for another 3 years before it became stuck in loose sand. Again, the engineers began working with a replica which they placed in an identical situation. When nothing was able to free the rover, it was declared a stationary research platform. Further attempts were made to position the rover so its solar panels could operate more effectively, but even this was not possible. The last communication from Spirit was in March 2010. Opportunity lasted until June 2018, when dust clogged its solar panels. In March 2006, NASA's Mars Reconnaissance Orbiter arrived at Mars and began the now routine business of aerobraking. Though this procedure took roughly 6 months, the saving in fuel will see the craft functioning at Mars into the 2030s. One of the primary functions of the new orbiter is as a communications relay station. Its 3-meter antenna transmitting in the ultra-high frequency band enables very high data rates. By November 2013, it had tripled the amount of data sent to Earth by all the other NASA missions combined. Its high-resolution camera began revealing the surface of Mars in the finest detail. These are active falling dunes in East Coprates Chasma. The polar region, free of the seasonal dry ice, again surrounded by dunes. In the southern hemisphere, pits in the residual cap of carbon dioxide. The poles of Mars were now attracting keen interest. Follow the water had become NASA's catch cry. The Phoenix lander was targeted at the northern polar region to follow up on information from Mars Odyssey suggesting frozen water lay beneath the surface near the poles. Because imaging had revealed the region to be unvarying, a rover was deemed unnecessary. The lander had been designed to use a parachute to decelerate, with rocket thrusters to deliver the craft to the surface, unlike NASA's previous 3 rovers, which had bounced. This decision proved controversial, as one strand of research suggested the rocket fuel would contaminate the very area that the lander was tasked with analyzing. The craft waited 15 minutes to allow any dust to settle before it deployed its solar panels. Phoenix had landed during the early spring in Mars's northern hemisphere, so the solar panels would receive plenty of light for the planned 90-day mission. As well as its camera mast, Phoenix was equipped with a meteorological station that recorded the daily weather. It featured a wind indicator and pressure and temperature sensors. In addition, a vertically pointed LiDAR was able to observe cirrus clouds forming in the region and snow falling in the polar atmosphere. These phenomena had not been observed before. The lander also had a robotic arm that could dig half a meter into the soil and deliver samples to the analyzer, a combination of 8 high-temperature ovens and a mass spectrometer. In one excavation, the cameras recorded a white substance which gradually disappeared. Given the temperatures and the time it lasted, it could only have been water ice that sublimated after it was exposed. The soil was slightly alkaline, and the presence of perchlorate, which kills bacteria, was not good news for those hoping for Martian life. Phoenix operated for 2 months longer than planned before the gathering winter completely shaded its solar panels. While the planet still had subterranean deposits of ice, there was precious little left at the surface, yet it was now understood that many of the red planet's features had been carved by running water. Samples analyzed from across the planet affirmed that water and nothing else had made these changes to the Martian landscape. Mars had once been more like Earth, yet it had lost its surface water and most of its atmosphere, and the question of life persisted. Could it have emerged in a warmer, wetter past? And could it still be present below the surface? The next Mars mission would be NASA's most ambitious yet. Known as Curiosity, the car-sized rover would be powered by a nuclear battery, making it immune to the dust problems experienced by Spirit and Opportunity.
7, 6.
Curiosity was launched on an Atlas V from Cape Canaveral in November 2011.
1. Main engine start. 0. And liftoff.
In mid-2012, it entered the Martian atmosphere heading for Gale Crater. The Jet Propulsion Laboratory monitored the entry closely, but had no control over events. In Mars's thin atmosphere, the parachute could only slow the heavy craft to around 320 kilometers per hour. Nearing the surface, the rover descent stage dropped out of the aeroshell and rockets kicked in. At this stage, radar was guiding the lander to the surface, and a small camera was recording images of the terrain below the rover. Next, Curiosity was lowered on a tether beneath the descent stage. This sky crane technique was used to avoid too much swirling dust exposing the rover to unnecessary danger. Everything had worked exactly as it was supposed to, and the American engineers were relieved. The landing had been the most precise ever. Before Curiosity could start work, its computer went through a checklist to make certain that all systems were operating correctly. It was a day before the rover deployed its camera mast and communications antennas. It's thought that Gale Crater is 3.5 billion years old, and that its sediments have been laid down first by water and then by wind. NASA now has a sophisticated mobile science laboratory on Mars, connected to Earth by the most advanced communications link, courtesy of the Mars Reconnaissance Orbiter. The rover's primary objective is to discover if conditions suitable for life ever existed or still exist on Mars. It's also gathering detailed information about the current conditions on the red planet, particularly the radiation levels that will have an impact on proposed manned missions. Curiosity has analyzed the dust from a number of holes it drilled, revealing sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, all elements essential to life. In its 6 years on the surface of Mars, Curiosity has traveled around 20 kilometers, but the driving is taking its toll. It routinely sends back a series of self-portraits, mainly for diagnostic reasons. Its wheels have taken severe damage, which will undoubtedly lead to design changes for future rovers. Its computers are also giving problems, but a new suite of missions is slated to arrive at Mars in 2020 that will continue profiling the planet. There is one aspect of the Martian environment that has never been investigated, but that's about to be addressed. The Mars InSight probe has been targeted at the flat Elysium Planitia, close to the equator, to spend 2 years investigating the planet's interior. It made a flawless landing in November 2018. After unfurling its solar array, it spent weeks selecting a suitable spot to deploy a seismometer onto the surface to monitor Marsquakes. It's clear that Mars had a warm, wet past, but it's cold and very dry now. Learning about the planet's geological activity will help us know why Mars has changed. The InSight probe also hammered a thermal sensor into the surface to gather data on heat flow from the planet's core. By understanding processes within Mars, we can learn how the geological histories of Mars and Earth began to diverge. One of the Sentinel Earth-observing satellites. They occupy low Earth orbits that take them over the poles. In similar orbits, the swarm satellites monitor changes in the Earth's magnetic field. In a much higher orbit, the GOES weather satellite hovers above the United States. It orbits at the same rate that the Earth revolves. The New Horizons probe does not orbit anything. It was launched on a flyby mission past Pluto, and it continues into the Kuiper Belt. Satellites are expensive. Designed to operate at extreme temperatures in the vacuum of space, they cannot be maintained. They must perform faultlessly for years. Yet every satellite depends on the brute force and precision of a launcher to deliver it to an exact orbit.
Top.
Launchers are expensive too. They have varying capabilities and varying reliability, but new developments in rocket technology are changing what can be achieved and how much it will cost. The days of giant state-owned corporations launching their own satellites are over. Rocket builders sell their services to commercial or government clients. In October 2014, an Antares rocket built by Orbital Sciences was set to ferry supplies to the International Space Station. The launchers are generally reliable, but space is difficult. There is still a 7% failure rate. This fundamental step of leaving the Earth's surface relies on a small group of international companies that build heavy-lift rockets. The most iconic booster in operation today is the Russian Soyuz. It's not the biggest or most powerful launcher, but its history stretches back to the earliest days of space exploration. Variants of the Soyuz launcher have been in continuous production since 1957, and they have made more than 1,800 trips to orbit. Since the demise of the Space Shuttle, the Soyuz remains the only human-rated launcher in operation, and both ESA and NASA rely on it to ferry people to and from the International Space Station. It is a direct descendant of the Vostok launcher that sent the first man into space. On the 12th of April 1961, Yuri Gagarin rose to orbit on Vostok 1, designed by Sergei Korolev. The design, featuring a central core surrounded by 4 strap-on boosters, was originally conceived as the first nuclear missile. But as Soviet warheads became lighter, the launcher was adapted for manned trips to low Earth orbit. Today, 4 variants of the Soyuz launcher are in operation, and they launch from 4 different sites. Many of the simple design features in the Soyuz have contributed to its reliability and low cost. It was estimated that Russia could launch 20 expendable Soyuz carriers for the cost of 1 space shuttle launch. Though the basic layout of the Soyuz is still recognizable after 60 years, it has evolved. The design has seen several generations of engine upgrade, with the guidance system continually being refined. Final assembly at the launch site sees the 4 distinctive boosters flanking the central core attached first. In Russian, they're known as carrots. Each booster and the core have one rocket motor discharging through 4 main fixed chambers. For guidance, the boosters have 2 additional small swiveling nozzles on their outer edges, while the core has 4 guidance nozzles. With the boosters and central core united, the assembly is now lifted onto its specially adapted railway truck. At this stage, it weighs just over 20 tons. When it's fueled, it will be more than 250 tons. The 4 boosters are known as the first stage. Even though they ignite at the same time as the central core, that's known as the second stage. Then, if the assembly is taking place in Russia or Kazakhstan, the third stage and the payload are fitted. This is the gamma-ray astronomy satellite Mikhailo Lomonosov, being prepared for the first launch from Russia's new cosmodrome at Vostochny in Siberia. The launcher and satellite are all assembled horizontally, a technique that is straightforward and practical. At Baikonur, the original Soviet launch site still leased by Russia from Kazakhstan, rollout usually happens at dawn. Baikonur is the only launch site where the Soyuz can carry a human payload. All of the Soviet Union's history-making flights started from the Baikonur Cosmodrome. The area's sparse population was one of the main reasons the Kazakhstan location was chosen. The rocket is delicately moved towards the firing ring, where it will be held in place by the 4 tulip petal arms. It takes about 1 hour to bring the launch vehicle to the vertical. As the lifting arm withdraws, the 4 support arms are joined by fuel and electrical umbilicals and 2 halves of the service gantry. Ground staff will have access to every part of the launcher, and the cosmonauts will enter their spacecraft via this gantry. Technicians will spend the next 2 days checking the rocket and preparing it for launch. When fully loaded with fuel, its weight will increase by a factor of 15 to 305 metric tons. Soyuz carrier rockets also launch from the European spaceport at Kourou in Guyana, and from here the rocket is erected without its payload. Because of the equatorial location, the Earth's spin makes it easier to reach orbit. A Soyuz launched from Kourou can lift considerably heavier payloads to orbit than it could from a Russian launch site. However, Kourou's tropical location has 10 times the annual rainfall of Baikonur, and a mobile gantry that protects the rocket is necessary. Like the other European launchers, the satellite is attached to the Soyuz while it is vertical. 5 hours prior to launch, the fuel is gradually introduced. The liquid oxygen boils at minus 182 degrees C, and it is constantly replenished. At 36 seconds, the first umbilical mast retracts, leaving the rocket on internal power. Soon after, the fuel connection swivels away, and the turbo pumps begin feeding fuel and oxygen to the engines. The engines are closely monitored as they are gradually brought up to full thrust.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top, décollage, lift off.
A guidance computer in the third stage maintains the launcher's attitude via the vernier nozzles around the first and second stage chambers. Near the 2-minute mark, the boosters shut down and are jettisoned. At 85 kilometers, the payload fairing splits and falls away. 5 minutes after liftoff, and at a height of 169 kilometers, the third stage takes over to accelerate the satellite and its upper stage to escape velocity. Less than 10 minutes after launch, the upper stage guides the satellite to its designated orbit, while the rest of the launcher falls back to Earth. The American Delta IV Heavy is designed to orbit massive payloads or to hurl probes out of Earth orbit at incredible speeds. When it first flew in 2004, it had the greatest lifting capability available. The first and second stages, as well as the two boosters, are all powered by cryogenic hydrogen and oxygen. It can lift more than 28 metric tons to low Earth orbit. The Delta IV Heavy is made by the United Launch Alliance, a collaboration between Lockheed Martin and Boeing. It was designed to meet US military requirements. It has launched 2 NASA missions, but its other 8 launches have been classified reconnaissance satellites. Services have not been sold to commercial clients. Recently, a Delta IV Heavy was prepared for perhaps its most significant launch. It was mated with the Parker solar probe and its star upper stage. The Parker probe will be the first satellite to fly into the Sun's corona. And though its launch weight of just 685 kilos may seem puny for such a large launcher, Parker must leave the Earth's orbit at near record speed. After a brief period in a parking orbit, the second stage reignited to break the bonds of Earth's gravity. The final kick, delivered by the solid-fueled upper stage, gave the Parker probe the second fastest departure from Earth, and with the help of the Sun's gravity, it will reach 668,000 kilometers per hour, making it the fastest man-made object ever. In 2001, SpaceX founder Elon Musk hatched a scheme to establish a greenhouse on Mars and began trying to buy a Russian launch system. The space industry laughed, but they're not laughing now. Because he couldn't buy a rocket, he built his own. Musk knew American launches were too expensive, and a little research convinced him he could undercut the established aerospace giants. In design and manufacture, SpaceX focused on simplicity and reliability, with a view to keeping costs down.
Of the Falcon 9 rocket and the Dragon spacecraft, packed with science and supplies for the International Space Station, humanity's home in low Earth orbit.
In 2012, SpaceX flew the first commercial resupply mission to the International Space Station. SpaceX designed its own spacecraft, the Dragon, to carry out these resupply missions.
Let's use some contact with a test 1.
To date, SpaceX has completed 11 successful supply trips to the ISS, with 7 more booked. Unlike all the other cargo ships that visit the space station, the Dragon is capable of returning to Earth. The Falcon 9, the company's workhorse, was criticized because it has 9 separate rocket motors. Old rocket engineers argued that there were too many moving parts with a higher risk of failure. The Merlin engine, developed for the original Falcon 1, continues to be refined, giving the Falcon 9 a steadily improving lift capacity.
Past the speed of sound, it's now subsonic.
Soon it became clear what the multiple engines could achieve. Without its fuel load, the spent first stage falling back through the atmosphere was very light, and just one engine could enable a soft landing. If this worked, it meant reusable stages would drastically cut the cost of launches. A pinpoint landing on a remotely controlled barge required so many new techniques, and space experts were skeptical. A landing leg had collapsed and was redesigned. Soon, these return trips were routine. Though landing capability reduced the maximum payload by 30%, it also drastically reduced launch fees. Next came the Falcon Heavy, essentially 3 Falcon 9s strapped together. In 16 years, SpaceX had gone from laughingstock to builder of the world's most powerful launch vehicle. This first flight was to be a pure demonstration. Its dummy payload was Elon Musk's red Tesla Roadster. The car would go into orbit around the Sun. The plan called for the 2 boosters to land back at Cape Canaveral. The central core would return to a barge at sea. Potential customers were watching the demonstration closely, and crowds who gather along the Florida coast to see a launch now wait to watch boosters returning. The car, rigged with cameras, went into a solar orbit, but in the mission's one failure, the central core missed its barge. The US Air Force will be the Falcon Heavy's first paying customer. The entry into the launch market of a company aggressively trying to reduce the cost of access to space is changing the space business. Today, SpaceX remains the only launch provider that openly publishes the cost of its services. The Ariane 5 is the European Space Agency's heavy lift rocket. It features a liquid oxygen, liquid hydrogen first stage, flanked by 2 solid fuel boosters. Though the Ariane 5 is not the most powerful launcher, it holds the record for heaviest payload to geosynchronous transfer orbit. The equatorial launch site in Guyana makes orbits of low inclination easier to achieve and is an attractive feature for paying clients. The Ariane 5 ECA is the 5th and final version of the 5 series, which will soon be replaced by the Ariane 6. A new version of the Vulcan rocket engine is being developed for Ariane 6, which will be cheaper to build and to launch. New facilities are being constructed for the Ariane 6 at the Kourou spaceport, including a new vehicle assembly building which will see a change from vertical to horizontal integration. But the Ariane 5 still has much to do. 18 launches are scheduled before its replacement begins flight testing. The stages are fabricated in Europe and cross the Atlantic by ship. At the launch site, the central stage is raised to the vertical. Slightly more than 30 meters long, the core stage is essentially a fuel tank divided into 2 compartments with a rocket engine at its base. Each solid fuel booster arrives on its table in an upright position and preloaded with propellant. The upper stage, that will on this mission deliver 4 Galileo navigation satellites to their target orbits is fitted. The satellites, clustered about a central dispenser, are then attached to the upper stage before the fairing that protects them during the trip up through the atmosphere is lowered into place. The Ariane, on top of the launch platform, begins its journey at a snail's pace. The Ariane 5 is operated by Arianespace, who have launched more than half the commercial satellites in operation today. Russia's heavy-lift Proton launcher started its life in 1965. It was originally designed to carry a 100-megaton thermonuclear weapon to targets in the US. It was never deployed as a missile, instead evolving into a successful heavy launcher. It delivered several modules to the International Space Station, and one of its recent high-profile successes was the launch of the first ExoMars probe. But the Proton has not been without its problems. Developed during the Soviet era, its manufacturer Khrunichev was reliant on the Ukraine for key components. And when launched from Baikonur, the Kazakh government was not keen on the extremely toxic hypergolic fuel it used. There are claims that acid rain falls after some launches, and that parts of Russia and Kazakhstan are being poisoned by the unsymmetrical dimethyl hydrazine that powers the Proton. At Baikonur in July 2013, a Proton M was set to launch 3 Russian GLONASS navigation satellites. An investigation found that the rate gyro package had been installed upside down. It was not the only recent Proton failure, and questions about quality control were being asked. Though the Proton still has launch commitments for several years, it will be phased out. Startup company Spacelab is poised for its first commercial launch. Their rocket, called the Electron, can deliver light satellites to low Earth orbit at prices that completely undercut the rest of the market. The launcher makes extensive use of carbon fiber in the construction of the tanks, and Spacelab has developed an engine with a radically new fuel cycle. Named after physicist Ernest Rutherford, the engine is largely constructed with 3D printing techniques. The liquid oxygen RP-1 fueled unit uses brushless electric motors to operate its turbo pumps instead of pre-burning fuel for the same purpose. The batteries powering the process add weight, but they save on fuel and give engineers finer control when throttling the engine. The launch site on New Zealand's North Island Mahia Peninsula is perfect for the busy schedule that Rocket Lab envisions. With the advent of microsatellites, smaller carriers like the Electron are becoming an attractive launcher for a new area of the launch market.